Hello, everybody. My name is Camus. Thank you for attending my talk, Going Beyond Alchemy, In-situ Analysis of Perovskite Growth by Optical Reflectance. This is talk about the latest results that LayTec obtained together with Camus Center Berlin. So let me give you a quick outline. I'll start my talk with an introduction, then I'll come to the motivation, the experimental method, and present some results about spin coding. Then I'll come to results about annealing. However, those will be presented in greater detail at EUP cycle later this year. And then I'll end my talk with a summary and outlook. I'll acknowledge my references. Let me briefly introduce LayTec. We're a Berlin-based integrated metrology company for various industries and markets. So we have solutions for the lighting sector, in LEDs and lasers, but also offer products for functional glass manufacturing, power devices, and of course photovoltaics. In all these markets, we address the processes at very different stages. So there's inline solutions that analyze the processes in between process steps on the conveyor or on the rotary lab. There's in-situ solutions that analyze the processes right as they occur during the process, and there is mapping stations or at-lab stations that do post-deposition analysis of the entire sample with respect to the spatial distribution of the distinct parameters. All of these methods imply our core IEP, which is the materials database with all the dispersion and process-related or material-related information about the materials. And they all employ our proprietary software and analysis methods. So now let's come to the motivation. So why do we think it makes sense to analyze perovskites in greater detail? Well, the answer is quite simple. If you look at the efficiencies of perovskites and their evolution during the last years, it's certainly the most rapid evolution that has been there in the history of PV. And if you compare the efficiency of the best devices for the particular technologies to the best silicon efficiency that's out there, you can see that in case of perovskite silicon tandem, this device has even outperformed already, and also other technologies are actually approaching this value. So it's a very promising technology. At the same time, perovskite provides excellent potential for driving down PV costs. As interestingly, for this technology, the low-cost methods are actually yielding the best efficiency, which is very different to other thin film technologies or silicon. These technologies can also be very easily integrated into existing silicon or CAGS production lines, but they could also be used for perovskite-only devices. So there's huge potential also on the economical side. So, but if everything's so great, why do we think we still need in-situ metrology? Well, we all know that there's significant challenges remaining. We still rely on toxic compounds. There's significant degradation. There's issues with scale-up, and most of all, there's a rather low predictability and reproducibility of those wet chemical processes, which is mainly due to their complex chemistry. This is why a lot of people are currently applying machine learning algorithms, but those mainly rely on the chemical structure or IV data, and what's actually missing, or what's the missing link, is that data in between that actually tells you something about the process that is going on in the real world. And this is exactly what we think in-situ data can do. This is the job it's made for. It helps you to understand all the details that are going on during the process, and this is why we think it's a very important part that's needed to accelerate this technology. So now let's come to the actual experiment. This is the sketch of our setup for spin coating and annealing. On the left-hand side, there's a spin coating setup. We had a perpendicularly mounted head on top of the spinning setup. During drop casting, we were using white light reflectance, and all the analysis relied on the specular reflex, whereas for annealing, we had a slightly off-axis angle for the measurement head, and so we only collected the diffuse light and avoided the specular reflex. But again, this will be covered at PVSC in greater detail. And for spin coating, here's an image of our real-world apparatus that was used. As you can see, it's rather simple with a spin coater down here and the optical fiber head right above it. And you can also see the samples that were deposited in that process. We applied our method to very different solutions that are relevant in the technology today. The spin coating process employed acceleration time from 0 to 4,000 RPM of 5 seconds, and the final rotation time was then in the range of some minutes. The metrology system itself was a prototype of LayTec-inspired system employing a tungsten lens for excitation and a CCD detector array from 390 nanometers to 1,100 nanometers for detection. It employed an optical hack with focusing optics, and the working distance was in the range of some tens of centimeters with a spot size of some millimeters and integration time for spin coating well below 1 millisecond and some tens of milliseconds for annealing. This is the first results for spin coating for the example of a triple cation complex for spin coating at 4,000 RPM. So the core piece of data that we obtained during our processes are such spectrograms in which the color-coded reflectance intensity is plotted versus wavelength, and then those spectra are aligned against time. And these spectrograms are just containing a huge variety of information about your process. For instance, while the precursor solution is still at rest, you can already see the initial absorption edge of the solution. And now as the rotation starts, you can see that clear changes start to occur, and you can resolve all the details even at this short time scale. So you can see the shift of the absorption edge during spin coating, and you can see the evolution of those interference fringes that evolve even further until only very few fringes fit into your film. And then at a certain point, there is a vanishing of all the interferences due to the full consumption of the solution, and the perovskite surface being too rough for constructive interference thereafter. So here's a very similar example for spin coating of MAPI and tribromide solution, and we're obtaining a spectrogram which at the first glance is quite similar, but interestingly here, after the end of rotation, the interferences persist and actually keep changing, and so there was a restart of rotation, and afterwards indeed the interferences kept changing until they were completely vanishing at the end of the process due to the full consumption of the solution. But that means that in the meantime, interferences persist and the process was in a kind of uncontrolled stage, which is something you certainly don't want, and this is something that can be revealed by in-situ data. So this analysis already shows you quite a lot about your process, but you can also go into quantitative analysis, which is shown on the next slide based on a paper that has just been submitted by my colleague Camus recently, hopefully published very soon. So you may refer to that for greater detail. I will only give a very short sketch about the idea. In principle, if you look at those spectra, you can deduce a film thickness by analyzing the distance between the interference maxima or minima. And here we did a rather crude approach by neglecting all dispersion and differences in the refractive indices, and assuming that the entire film was broken by the interfering light. If you do that, it basically means that the final thickness corresponds to the time at which the interference will start to vanish. And it turns out that this thickness agrees very well to post-deposition profilometer measurements, which we did after completion of the process. So usually we have some 100 nanometers film thickness, and within the margin of error, both measurements agree quite well. So what does it mean? It basically means that indeed interfering light seems to probe the entire film, so the solid part and the liquid film, while the liquid film seems to act like a reflection agent, enabling the dominance of the interfering light over the scattering light. But as soon as the illusion is more and more consumed and is not covering the solid film completely, scattering starts to dominate and there is no interference observed ever after. This would mean that this thickness here, xn, is basically the thickness that you would measure at this point here at the last spectrum that is obtained. So it would be kind of the maximum thickness of your film topography, which also fits the fact that we have a good match with the profilometer measurement, because this is actually what you would expect for profilometer measurement. So if we now summarize the results for spin coating, we can say that in-situ reflective data reveals the evolution of the absorption edge or the bandgap of the liquid and solid film, as well as the evolution and the final thickness of the liquid and solid film, or the incompleteness of solid evaporation. We also saw that the interferences vanish as soon as scattering dominates over specular reflection due to the rough film surface, and that the final thickness agrees very well to post-deposition measurements of the film thickness. So that means that in-situ reflectance gives an almost complete record of deposition process, which can be used for modeling, quality assurance, or training of machine learning algorithms. Just very briefly, I would like to address the annealing results as well. Here we were also able to monitor the absorption edge of the perovskite films. It was a very good fit to the PL obtained from these films. It worked for all films, and again, it visualizes if your process is too short, too long. It helps you optimizing the process conditions. So here's just a quick comparative result for bandgap monitoring in the case of annealing. For FAPI on the left-hand side and MAPI on the right-hand side. On the left-hand side, you can see a process as you would expect it. After some seconds, the absorption edge shifts to the value that you would expect, and then stays at that point for the rest of the process. Whereas for MAPI, similar process occurs at the beginning, but then there is some parasitic absorption popping up, which is something you certainly don't want in your optical device. So this calls for further optimization and was revealed by in-situ data. But again, I will tell you more about that in my talk at PVSC. Let me summarize my talk. We showed that the monitoring of perovskite thin film formation on the millisecond scale is meaningful and feasible. We showed that you can directly monitor the thinning of the precursor solution, directly deduce the film thickness of the precursor. You can monitor the absorption edge of the solution during deposition, as well as the bandgap of the layer during drying, and you can detect secondary phases and optimize your process times and conditions. And by that, you can generate input data for machine learning and modeling. In the future, we would also like to have a look at near infrared and for deposition on top of silicon or by means of other deposition techniques. So this is the end of my talk. Thank you very much. And these were the references that I used. I'm happy to hear from you if you should have questions or comments. Thank you very much.